completely optional. All the lectures are completely optional. But this one is even more optional. To the effect that if you feel like you will be spending good time by solving some problems and asking some questions, then it's good for you. Otherwise, you'll probably be spending your time better by doing something that gets you studied for some other test or gets you ready for something, prepares you for your weekend of studying. Right, so this is a completely optional session and it's going to be driven by you guys. In other words, I will only bring up questions and put them on the board if lethargy, which I hope is not going to happen. We had some questions yesterday and it worked out quite nicely yesterday. It was a much smaller class than it is today. So let's see how it goes. Has anybody got a question? Okay, so the question here to explain about the Big Bang penny story. If you will recall, the best way to explain this, in fact, is to solve the motion of a compound pendulum. So let's do that first. And then we'll realize that a compound pendulum, its motion is independent of its mass. So let's take a pendulum. Any object will spin around with its mass. And we'll spin it. We'll rotate around that axis just like we rotated the simple pendulum around. Now when we take this guy, let's say that we parameterize it. How should we start? I give you this, a blob on a page, and an axis around which I'm rotating. And I tell you, solve for the equation of motion in terms of the moment of inertia of the thing when it's rotated around that point. What do you do? Find the center of mass. Okay, so let's draw in the center of mass. Let's say it's here. In fact, let me draw it differently. This is the center of mass. System. Now what? Moment of inertia. Okay, so we know we're going to find the center of mass. We know that we're going to find the moment of inertia. This around which point? Around the axis, right? So let's call this I. Center of mass. How can I even write anything down unless I have a coordinate system? So the absolute first step would have been to draw some coordinate somewhere. Generally, we take a point about which we're pivoting it, and we put in the y-axis. Yeah. What's the question? The question is, I've got that blob over there. I've got a blob. Object. Any object. Oh, potato. Potato. And I'm taking it. Let's take this book since I don't have a potato on me. And I'm doing this. I'm letting it spin like a pendulum. And I'm asking, how would you go about solving this problem? The actual question was about Big Ben and the penny, but we've got to get there by degrees. The first step is to look at this, what we call the compound pendulum. Right, so we have a suggestion that we should look at the moment of inertia and then we can find the center of mass, which we can now do in terms of whatever coordinates we've chosen of the actual object. What do we generally do when we solve problems with regard to mechanics? What do we have to find? Degrees of freedom, that's good. So, how many degrees of freedom does this potato have? Who says none? I'm very glad that nobody puts their hand up for that question. Who says one? So the rest of you It is one. It's a pendulum after all. It's just rotating up and down. Can't spin or anything funny. It has 1 degree of freedom. What's next? Generalized coordinates. Well, that's a good question now. It's no longer just a bob on a rod. It's a general blob, a potato, a book, something. How do we define my generalized coordinate? So someone says theta. Where do I draw the theta?
Draw a line between the center of mass and the axis.
Okay, let's draw a line between the axis and the center of mass. To be clear, that's the center of mass and that's the axis. Wondering. Okay, we've drawn that line, and now what?
Draw a line between the axis and the axis.
And we want to vertical line. And theta's the angle between them. We all happy with that description? Right, so now we have, for any object, defined an angle theta so long as we can draw a line between the axis and the center of mass. Great, so we'll say our generalized coordinate is theta. Let's say that the moment of inertia I has a form that looks like mL squared. Those are the dimensions of moment of inertia, if you think about it for a second. Those are the dimensions of the moment of inertia. So I'm going to just say it has that, where L is some value that gets computed as we word it. Maybe let me not call it L. L is too suggestive. Maybe we call it, I don't know, or there's nothing that could look like a radius here. So those are the coordinates, and I'm just going to call it this. This R squared obviously is something that will be computed in terms of the geometry of our shape, which is unknown, and so we cannot compute this. If it was known, if this blob was a specific object, like a square or a rectangle, then you could certainly work this out. Now, the question is, we're given this. What's next? Transformation equations. Now, transformation equations are a bit of a difficult one because this is a compound system. We can skip that step. We need the transformation equations in order to go to the next step normally. And the next step normally is computing the kinetic and potential energy. We can get them directly because the kinetic energy and potential energy are given in terms of the moment of inertia and center of mass. So let's work it out. The kinetic energy is very simple. This object, is it translating and rotating or just rotating? Just rotating. So we don't need to worry about the translational component. It's just a half I omega squared, which is a half, and I is m r squared times by theta dot squared. Now we can write the potential energy down. The potential energy is mg times the height of the center of mass. What is that? The height of the center of mass from my axis, from my point, my reference point, goes downwards, so it will be negative, and it's this distance here, which is what? I've got cos theta coming out, I've got alpha theta, I've got an mg cos theta. So we need to decide, people are saying oh, right? We need to define this distance between the center of mass and the axis. Let's call it L. So negative L cos theta is HCOM minus mg L cos theta. Alright, so that's all very simple. We can now write down the Lagrangian. The Lagrangian is simply 1/2 mr squared theta dot squared plus mg L cos Right. So the equation of motion, which is the next step, is something we can compute by simply taking the appropriate derivatives, working out the Lagrange's equation. Right, so d by dt del L by del theta dot is equal to del L by del theta. And that is, in this instance, del L by del theta dot is you write the equation down. That's equal to d by dt del L by del theta dot is simply del L by del theta and now we can work out this derivative. What do we get? mr squared theta double dot is equal to minus mgl sine theta. And we can work out theta double dot, mass cancels. We can get rid of it. Those of you who were here yesterday will have noticed that in the Lagrangian mass is a constant common factor, and therefore the equations of motion are independent of mass. Those of you who went today's oral test will further know that there are other ways of simplifying Lagrangians. They are quite powerful. Right. Theta double dot in general here is then equal to minus g L over r squared sine theta. So I'm going to write this in a suggestive way. I'm going to say theta double dot plus g over r squared over L sine theta is 0. Why did I write it like that? Because it looks like the motion of a simple pendulum. Correct. So the simple pendulum, if you recall, was theta double dot plus g over L sine theta is equal to 0. So we find that this pendulum moves, this compound blob thing, moves in the exact same fashion as a simple pendulum, but with an effective length, a length determined by both the moment of inertia and the distance between the center of mass and the axis in my particular problem. And we have an effective length, L effective is equal to r squared over L here. So we can rewrite this equation in exactly the same way as a simple pendulum, provided L is L effective. So what do we realize? A couple of things. Firstly, for a simple pendulum, all the mass is concentrated at the center of mass. And if you work everything out, that essentially means that R and L are equal. And when R and L are equal, R squared over L is equal to L, the length of the simple pendulum. So this does reduce correctly. Secondly, it says that everything that you take and swing around an axis ultimately does the same thing. It does what you expect it to do. It swings. And it swings as though it were a simple pendulum, with all of its mass concentrated this distance from the axis of rotation. Another thing that I must emphasize, particularly at this point in reference to the question that we had, is that the simple pendulum, and all of these pendulums, their equations of motion are independent of the mass of the system. There is no m here. There is no m here. In other words, if I took a potato and I pumped lead into it, and I swung it around the axis. Provided that I pumped lead in a uniform fashion into that potato, it would still swing like a potato. So we are compelled to sound like the old sheriffs of old and say, doesn't matter who you are, you still swing the same. Yeah. So R is not a name. R is something that you get from working out the moment of inertia. And the reason why I put R squared up there is because the moment of inertia has dimension, mass times length squared. So I'm just taking some fundamental dimensional constant. When you work out the moment of inertia, it will look like mass times something. And that something, when you square root it, for whatever geometry you have. Okay. So now that I've said that, I'm going to outline this problem for you. The problem that was the question that was asked. It was the following. Big Ben in London is a pendulum clock tower. So they keep the time basically by swinging this long pendulum. I mean, it's meters and meters long. And just like this potato, it swings in the same way. It has the same equation of motion. It's independent of mass, its equation of motion. And if its equation of motion is independent of mass, every feature about the motion is independent of mass. In particular, when you take the small angle approximation here, and then you solve for the period, or even if you don't take the small angle approximation, you solve for the period of the pendulum, that period will be, because obviously the theta itself is going to be repeating, right? And the period is the distance between successive points of the same time, the same point in the cycle. Now that period, that time distance, is completely dependent on this equation. And if this equation is independent of mass, then the period is independent of mass. The mass of Big Ben is irrelevant. If Big Ben was made of marshmallow and there was no air resistance, then we imagine that it would behave in the exact same fashion that it does, being made of iron and copper and brass. So the question is, why does the following work? There is a tray at the back of Big Ben. So here's your clock pendulum, and if you were behind it, sitting inside the clock tower, there's a little tray here. Very tiny tray for an enormous pendulum. And on that tray, the manager of the clock tower can place a single penny, if he so desires, or a couple of pennies, in order to change the properties of the pendulum. When he places the penny on the tray, he does so in order to change the time. Let's say that Big Ben is 1 second fast. And all the movies being filmed in London are now showing the wrong time, and it's a tragedy. So the manager of the clock tower has to come along and change the timing of Big Ben. Change the period just slightly so that the timing is back on track. And he does this by placing a single penny on that tray. Now we all agree that the penny will make the pendulum very slightly heavier. But hang on a second. That doesn't matter. There's no end here. So why does it work? That was the question that we were asked. And you've already answered it, so let's ask someone else. Yes. Mass distribution. Okay, so can you unpack that for me? The mass distribution changes the effective length. There you go. So, those two answers answer that perfectly. What happens is, yes, the mass doesn't matter. But adding a single penny down here, well, if this point is below the center of mass, it'll make L longer. If the point is above the center of mass, it'll make L shorter. What else? If there was some fundamental change to the radial distribution, then we would also change R. But I severely doubt that R will change, so long as we put this thing close to the central line of the pendulum. So what tends to happen is we're changing L. And by changing L, we're changing the effective length. So if I were to ask you a question, if I were to say, in a matter of fact, the tray on the pendulum is below the center of mass. And then I ask the follow-up question. Does adding a penny speed the clock up, or does it slow the clock down? That will be in the test on Monday. I will not say now. Think about it. The question is, the tray is below the center of mass. Assuming that the R doesn't change, does adding a penny speed the clock up or slow the clock down?
If you repeat the mass distribution, so there's a sudden significant change in the effective level, would that force it to jump ahead of itself?
It would. What they tend to do is they put the penny on and then they take it off once it's back. Right? So, but the idea is also contraction and expansion of the rod can cause the center of mass to lift and lower. And you have to account for that sometimes when you do expansion and contraction. It does cause a change. You could model this as a function of time. And then you can see how the change actually comes into being. Right, I'm going to take a note of that so that I can remember to ask this question in the test. So, below the center of mass, right, now I will be in the test. Are there any other questions? Or we all can go home? Yes. Yes.
How would that change the density of the function of time?
Time.
Or whatever.
Okay. Let me clarify that point. That's the point that I just want to clarify before I even answer that question. When I say the density is not constant, I mean it's not constant over the region. In other words, it's changing when you're here and when you're here. Generally, the density doesn't change with time in solid objects. Unless you're undergoing some heating process or some fundamental chemical change, the density tends to remain constant with time. I can't think of any exception to that rule. I mean, there's fluid mechanics, obviously. Let's keep to rigid body dynamics. So when we say the density is not constant, we mean I've got some object, and throughout this object it's maybe heavier here, maybe lighter here, maybe very light over here, right? And then you've got to ask questions like what's the center of mass, what's the moment of inertia, and how would you answer? That's your question. How would you now answer the question if the density is not? Right, so that was the question of today's oral test, okay? But let's treat it in the case of a hemisphere. So the first thing that you should always do when dealing with a non-constant density is you should know, you should ask, you should be told in what manner is it non-constant. Right? A non-constant density could mean all the density is here. It could mean the density varies radially from the middle. It could mean the density varies as the square of the radius from the middle, as the cube of the radius, as sine, absolute value of sine of the radius. You can do anything. And you can make it a function of the radius, you can make it a function of the height. You can play indefinitely these games of changing the density distribution and asking, in that case, where's the center of mass? In that case, what's the moment of inertia? Yes.
If the is no constant, like symmetric actions, like that.
Not always. That's a very good point. Not always. If the density was a function of x, for instance, then you can't expect something over here and something over here to cancel off unless that function is symmetric. Points diametrically opposed will only cancel if the density at those points are the same. If the density is different between point here and point here, it means that you can no longer use symmetry arguments. Very good point. Okay. I want you guys to tell me what my density is for this hemisphere. What density should we try? It varies with what? The radius, the height, the radius. Okay, let's do radius. Rho is a function of r. Okay, what type of function of r? Linear? Linear is easy, let's do linear. Let's say it's some constant times r. Now the first question that we have to ask is, what is that constant? And these things are always fundamentally underdetermined because we can work out the mass. And that's always the first thing you ever do with this type of question. If you want to work out the center of mass, if you want to work out the moment of inertia, the first thing you always do is you ask, what is the mass? So let me ask it. What is the mass? This will be the first thing you write down every time you solve this kind of equation. Now, we've got to expand that. How do we expand that? We ask, what does integral mean? What does dm mean? Well, let's answer those questions in one at a time. What does integral mean? Integrate over the region. What region? The hemisphere. Okay. If I'm integrating over a hemisphere, I must parameterize that. Which coordinates do I choose? Spherical. Good plan. All right. If I choose spherical coordinates, then what are the ranges of each of my coordinate parameters in order to parameterize a hemisphere? So let's stick with R instead of rho because rho is density. So R sits where? Between where and where? 0 and the radius of the whole thing. All right, what about theta? What about phi? So theta? 0. I've got heard pi and I've heard 2 pi. I've heard some pi over 2. So who says 2 pi? Who says pi? Who says pi over 2? Oh. We have quite an argument here. What is theta? Theta is the angle from the top down. That is